Hello guys. So today we are going to study about the paillier encryption scheme. First a bit of introduction. What is paillier encryption? Let's read. The paillier crypto system, invented by and named after Pascal Paillier in 1999, is a probabilistic asymmetric algorithm for public key cryptography. The problem of computing nth residue classes is believed to be computationally difficult. The decisional composite residuosity assumption is the intractability hypothesis upon which this crypto system is based. So basically, people, this is an asymmetric public key cryptography. What does it mean? First of all, the symmetric algorithms are the algorithms with single key, like we studied AES and DES, which have only single key, that is the private key. Now, asymmetric algorithms are the algorithms having more than one key, and in this case, it has a public key for encryption and private key for decryption. Now, it is similar to the RSA, but it has one distinct feature which is very important, and that is homomorphism. Now, let us understand what is homomorphism. What is homomorphic encryption? Now, what happens, like when you encrypt a message, suppose you have to add another encrypted message to it. So you will have to first decrypt both the messages, then add and then encrypt again the entire message. Now what this algorithm enable is that you can add the encrypted text both two encrypted messages to get the whole message as a summation of the two messages. So this is the X factor or the feature which gives us an edge over RSA. Now, as you can see in this paragraph, I'll read from the fifth line. RSA is the first public key encryption scheme with a homomorphic property. However, for security, RSA has to pad message with random bits before encryption to achieve semantic security. The padding results in RSA losing the homomorphic property. So that is why the paillier comes into the picture and becomes a very important algorithm, because it has a homomorphic property whereas RSA does not. Now, as in every algorithm, there are three basic steps: key generation, encryption, and decryption. Now let us study these steps for the paillier encryption scheme without further ado. Now, key generation. You see, the first step is to take two large prime numbers p and q randomly and independent of each other, means they should be unique. Now GCD of p comma q, that is GCD of product of pq and product of p minus 1 and q minus 1 should be equal to 1. This property is assured if both primes are of equal length. This is an important point here. Now we'll compute n, which will be equal to the product of pq, and lambda we'll compute, lambda is any variable, which will be equal to LCM of p minus 1 and q minus 1. Here LCM means least common factor. Now after we have done these computations, the next step is to select random integer g, where g belongs to the range zn square. N means the product of pq and pq square. Any integer in this range, in integer range of n square, we can take as g. Now we must ensure that the order of g by checking the existence of the following modular multiplicative inverse, which is in the right bottom corner, that is mu is equals to L of g to the power lambda mod n square whole inverse mod n. Now this mu is the modular multiplicative inverse. And you see here in mu there is a function L of g lambda. Now this L is a very important function, and it is defined as Lu is equals to u minus 1 by n. So remember people, this is a very important function. This is, I think, the very X factor which gives us an edge to this algorithm, and it will be very useful in calculations further. Remember this function. Note that notation a by b does not denote the modular multiplication of a times the modular multiplicative inverse of b, but rather the quotient of a divided by b. Very simple, a by b does not mean that a is being multiplied by the modular multiplicative inverse of b, but rather the quotient of a is divided by b. As simple as that. Finally, the public key will be n comma g. N is the product p into q, and g is a random integer we selected in the range zn square, remember. and the private decryption key is lambda comma mu, where lambda was LCM of p minus 1 comma q minus 1, and the mu was the modular multiplicative inverse. So these will be the two key which we'll get. Now a simpler case of this would be if we take g, the random integer, to be n plus 1, simply lambda to be psi n and mu to be psi n inverse mod n, where psi n is p minus 1 into q minus 1. This will be the simpler variant of the above key generation steps. Now let's move on to the encryption. Now let the message m to be encrypted where m belongs to the range of n. We'll select a random integer r. First take a message that needs to be encrypted. Then take a random integer r, just a 0. Now compute the ciphertext as c is equals to g to the power m, that is the message, into r, the random integer, to the power n mod n squares, where n is the product p comma q of the primes, and g, as we all know, is a random integer we selected in the range zn square. Now for the decryption, let c be the ciphertext to decrypt, where c will belong to the range zn square. Exactly, here we encrypted the text and c will belong to the range zn square. Now we'll compute the plain text message as m, the plain text message, which is equal to l, the function I defined, lu is equal to u minus 1. It is the same function. Bracket c to the power lambda, c is the encrypted message, mod n square into mu, mu is the modular multiplicative inverse, mod n. This will be the decrypted message. Now this is all theory. Let us do a practical example to understand the concept better. Here is a paillier example. Now let us take two primes, for example p equal to 7 and q is equal to 11. But in practical use, we have to take bigger prime numbers so that their product is much higher, and from the product it will be very difficult to reduce the two primes. So be aware of that. Then n will be p into q, that is 7 into 11, 77. First step, we find n. Next, an integer g must be selected from zn square, such that the order of g is multiple of n in zn square. Now we randomly choose the integer g as 5652. Then all necessary properties, including the yet to be specified conditions, are met. The order of g is 2310, that is 30 into 77 in zn square. All these criteria is satisfied. Therefore, the public key is n comma g. Now n is 77, that is 7 into 11, and g will be 5652. So now we get the public key. Similarly, to encrypt, m is equal to 42, where m belongs to zn. Then choose a random r. The r will be 23. We choose a random r in the range zn. Then compute the formula of encryption. C is equal to g to the power m r to the power n mod n square. Then all the calculations. So we get 4624 mod 5929 as the encrypted message. Now to decrypt this message, the first step is to find the lambda, because to decrypt we need a private key, and the private key is lambda comma mu. So lambda is LCM of p minus 1 and q minus 1. P minus 1 will be here 7 minus 1, that is 6, and q minus 1 will be 11 minus 1, and that is 10. So LCM of 6 and 10 is 30. Now as I told you, the very important function LU, here LU is u minus 1 by n. Now we'll compute k. K is equal to L g to the power lambda mod n square. L function, then g is a random integer which we first initialized in key generation, that is 5652. Lambda, the LCM to the power 30 mod n square. Now L of 3928. Now we'll use the LU function, that is u minus 1 upon n. So 3928 minus 1 upon 77. Thus we get k is equal to 51. Now we'll compute the inverse of a, which will be the multiplicative inverse. That will be mu. It equals to k inverse mod n. Therefore 74 mod 77. Now the message will be m is equal to L c to the power lambda mod n square into mu mod n. Now do the calculations and you finally get 42. Now you see the message was m is equal to 42 and finally after decryption we get 42. Now I'll give you a minute to just go through all this. Okay. Now as we have seen the example, now let us see some of the homomorphic properties. A notable feature of paillier crypto system is its homomorphic properties along with non-deterministic encryption. And the examples for this will be the electronic voting in applications for usage. You see the application, it is used in electronic voting or electronic cash. Now let us see the homomorphic addition of the plain text. The product of two ciphertext will decrypt to the sum of corresponding plain text. Now what do you understand? Like let the two message be M1 and M2. They are plain text. Now we encrypt M1 and encrypt M2 as in E of M1 comma R1 the random integer which we suppose in Zn and E M2 comma R2 the two encrypted text. Now when we'll multiply both the encrypted text mod n square and then decrypt them, what we'll get will be M1 plus M2 mod n, that is the product of two encrypted text. When we'll decrypt it, we'll get the summation of two plain text. This is the homomorphic addition. Similarly, when the product of a ciphertext with a plain text raising g, the integer we supposed in the range zn square, will decrypt to some of the corresponding plain text. Similarly, encryption of m1 into g to the power m2, when we'll decrypt it, we'll also get m1 plus m2. Similarly, as homomorphic addition, there is homomorphic multiplication, in which an encrypted plain text raised to the power of another plain text will decrypt to the product of two plain text. Let's see how. Suppose M1 is the first plain text and M2 is the other plain text. Now when we encrypt M1, that is M1 comma random integer R1, encrypt this, raise this to the power M2. Whatever the answer will be, raise that to the power M2. Then decrypt the whole, what we will get is M1 product M2. As simple as that. More generally, an encrypted plain text raised to a constant k will decrypt to the product of plain text and the constant. Similarly, when we decrypt m1 raised to the encrypted messages m1 comma r1, when we'll raise that to the power k, it will give k into m1. However, the paillier encryptions of two messages, there is no way to compute encryption of product of these messages without knowing the private key. So guys, this was the basic of paillier encryption, and it is a very important and practical algorithm. As you see in RSA, if you had to do such type of addition, then you had to convert the text first into the plain text, then add it and then encrypt again. Whereas the paillier gives us an X factor or an advantage that you can get the homomorphic addition or multiplication of two plain text by directly doing operations on the encrypted text. So thank you. Hope you understand a bit. Have a nice day.